Hey guys, I wanted to show you this neat example of using polar coordinates in double integrals. As you may or may not know, the antiderivative of e to the negative x squared does not have a closed form. So this particular integral would be impossible to do just as it is written here. Instead, we have a little trick for turning this into a double integral. So if we take this integral right here and set it equal to just some value, like a, for example, okay, then also a squared would be equal to the integral performed twice. But don't forget that when you integrate, the variable that you're integrating by is really just a dummy counter variable. So you can pick whatever variable you want. I'll be integrating from negative infinity to infinity in the second integral here with respect to y instead. So you'll notice a squared is still, it's a times a, but the integral that I've written in both spots, one of them is of x, one of them is of y, it doesn't matter because I'm just using those particular letters in those particular integrals. But now that they're multiplied, this is essentially an iterated integral. So I can bring them back together, the opposite of what we've usually been doing here. So in other words, a squared is also equal to the iterated double integral, both negative infinity to infinity on each of these, and it would be e to the negative x squared times e to the negative y squared dy dx, like so. Okay? From here, I could then remerge this back into a double integral. Remember how we would convert iterated integrals from double integrals? Well, we can do it in reverse too. No problem there. So I would actually here have the double integral, and notice the region that we're integrating over, all of y's and all of x's, right? If you put all of that together, that's really the double integral over the entire R2 plane. So that's our region of integration. And this would be e to the negative x squared minus y squared dA, right? Because dy times dx is a small infinitesimal piece of area, dA. And now I actually have a double integral, which is equal to a squared. But this particular double integral in rectangular form is quite disastrous. But if I convert it into polar coordinates, right, I can still go over all of the R2 plane, but converting this into polar will give us an extra piece that we didn't have before, right? So remember, right here, I can actually factor out the negative from these two, right? X squared plus y squared, it's just going to give me r squared, right? But then also don't forget in polar, the dA, the area element of integration, is r dr d theta. So here the integral then becomes the integral from 0 to 2 pi, and the integral from 0 to infinity, right? That's the theta one, that's the r one right there, and it's e to the minus r squared now. And then for dA, we have r dr d theta. Okay? Now notice what we now have that we didn't have before. We still have to integrate this same e to the negative variable squared just as we were originally. But now we have a times r to go with it, right? This has now become something much simpler than the original integral. This is now something that I can do with substitution in the R field of integration here, right? So let's rewrite this into the format that I'm telling you about here. The integral from 0 to 2 pi, right? And then inside of this, I have the integral from 0 to infinity, which I'm going to have to do with a limit, right? Definitely. Of r e to the negative r squared dr. And then d theta, like that. Okay? This integral right here, I can do with substitution, right? No problem whatsoever. No problem for the substitution there. I can take and just multiply the negative 1/2 here, and then multiply the negative 2 here, so that I have the proper substitution derivative there, right? And then don't forget, the antiderivative of e to something is still e to something, right? Okay, so then the next step in the integral here looks like this. Integral from 0 to 2 pi. Then I do the substitution integration here. That leaves me with a negative 1/2, and it's e to the negative r squared from 0 to infinity. And then I still have my d theta here, right? Still have the d theta. When I go from 0 to infinity, again, don't forget, the actual true way that I'm dealing with this infinity is I'm taking a limit as b, or whatever letter you want to choose, goes to infinity. I'm actually letting r, the limit as r goes to infinity there, whatever way you want to approach that, okay? But it's e to a negative infinity, right? The limit as r goes to infinity of e to the negative r squared, e to the negative r whatever, right? That's going to go to 0, right? That limit right here, the limit goes to 0 when you let e to the negative infinity, basically, right? So what I end up with here is the integral from 0 to 2 pi of negative 1/2 times 0 minus, okay, now let's plug in 0, right? E to the 0 is just 1, right? No matter what the power is. Anything times 0 is 0, and then you got e to the 0 is 1. So I got 1 d theta. Like that. Okay, well, 0 minus 1, hopefully still negative 1. I don't know, didn't go to the meeting, but I'm pretty sure they didn't change it, right? You got negative 1/2 times negative 1. It's just a half. I'm integrating 1/2 here, right? This whole value is just 1/2, right? So when I integrate 1/2, it's just 1/2 theta, right? 1/2 theta, and then it's from 0 to 2 pi, right? So 1/2 theta, but theta goes from 0 to 2 pi, right? Right? Good. So when I plug in 0, of course it's 0. I have 2 pi minus 0 for this. So it's just 1/2 times 2 pi. Which is pi. Okay? Now don't forget, what we originally had this equal to, this whole integral right here, was a squared. Right? A squared equals pi. What does that mean? A is pi with a square root. So square root of pi. Right? What did we originally say A was? The value of the integral itself. We said the value of this integral here was equal to whatever A was. And we just found A is equal to the square root of pi. Right? So this integral has a value, square root of pi. Okay? Now I know what you're thinking. Couldn't we try to do the same trick maybe and not do the negative infinity to infinity? Right? Tricky question there. Part of that negative infinity to infinity made this conversion as easy as it was into polar. Right? If this was some other rectangular region with other numbers that stop and are finite, then that region wouldn't convert as nicely into polar. The nice conversion here, part of that nice conversion, is the fact that I'm using the entire plane. And in both systems, the entire plane is the same object, right? Whereas if I were to do numbers here, trying to convert a rectangle region into some sort of circular region would mess up a lot of our niceness, right? So this is the one version that I can do, the negative infinity to infinity of that. And this is actually an important example in many fields of study. Probability, statistics, quantum mechanics is one, right? All right, guys, hope you enjoyed.